This question says, a certain substance X has a normal boiling point of 116.7 degrees C and a Molal boiling point elevation constant of 1.53 degrees C per m. Is basically what that says, per molal. A solution is prepared by dissolving urea, this is urea, in 700 grams of X. This solution boils at 118.3. Calculate the mass of the urea that was dissolved. So essentially, we dissolve some amount of this substance in 700 grams of X. The original boiling point was 116.7 degrees C, but now that we have some solute dissolved, the boiling point is 118.3 degrees C. And it wants to know what mass of this is in this 700 grams of this X, whatever the solvent is. So that's basically what we're going to do. Essentially, this can be done many ways, but I suggest doing it as a two-part problem. So first, let's find the molality using the boiling point elevation. So delta T B equals I, the Vant Hoff factor, times KB, the boiling point elevation constant, which is given, times M, the molality, which in this case is our variable. So the temperature, the boiling point went up from 116.7 to 118.3. If we subtract these two numbers, we found that the boiling point elevation, delta TB, is 1.6 degrees C. Equals I, the Vant Hoff factor. In other videos on this playlist, we talk about the Vant Hoff factor, but the Vant Hoff factor for a covalent compound, a compound which contains no metals, is 1. When you dissolve a covalent compound in water, it stays intact. Versus if you dissolve an ionic compound, like say NaCl in water, you would get Na plus and Cl minus. So therefore you'd have two species in solution, and the Vant Hoff factor would be 2. Remember that boiling point elevation and freezing point depression are colligative properties, which means they depend on the amount of the things in solution, the amount of these, but not the exact identity. Finally, KB. KB is given, and it's 1.53 degrees C per molal. This says degrees C per molal. Notice that it's upside down because it's divided by, times M, the molality. That's the variable. So essentially, we want to take 1.6 divided by 1.53, and we get molality equals 1.0458 molal. And we care about two sig figs, since our temperature change is two significant figures. Now that we know the concentration of the solution, we essentially have a dimensional analysis problem. And again, there are many ways to do this, but I'm going to do it using dimensional analysis. So we have a kilograms, okay, because this is moles per kilogram. We want to start with kilograms. We have to divide that by 1,000. So we have kilograms of X, the solvent. We want to convert that to moles of the urea, which is NH2, NH22CO. And then finally, to grams of urea, which again is NH2, 2CO. So this is a dimensional analysis problem, except we're going to use a molality instead of a molarity. There are many videos on this channel, or at least several videos on this channel, where we do similar things for molarity, but here we're doing it for molality. So let's start with our kilograms of X. We divide that by 1,000, and we get 0.0700 kilograms of solvent X times. Well, what this means is there are 1.0458 moles of the urea in 1 kilogram of X. So we put the 1 kilogram of X on the bottom and the 1.0458 moles of urea on the top. Then we just need to convert from moles to grams, times, we put 1 mole of urea on the bottom, and on top the molar mass, which is 60.06 grams of urea, which goes on top. multiply by the top, divide by the bottom, repeat, 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 and we end up to 2 significant figures. Remember that our molality is 2 significant figures. To 2 significant figures, we end up with 44 grams of urea in this solution. Some of the questions that I saw in this topic are more straightforward, and you're just solving for molality, or you're actually given the information where you can calculate molality, and you're solving for the change in temperature or the final temperature at which something boils or freezes. But in this case, it's actually you first want to find the concentration, and then use the concentration to find the mass of the substance that you need.